model something here. I need to pick a plane. Oh, let's pick the fine plane. That's a perfectly fine plane. And we're gonna go sketching, and I'm gonna go sketch. And I think I'm gonna make myself an arc, because the first thing I have you do is I had you make an arc that had some sort of radius on it, right? Come on. Where you got zero there? Okay. Okay, and then we go like that. There we go. Okay, I have an arc, right?
So how do you do that?
As a center point arc, I clicked on it and made myself an arc.
Three?
How come you have 3 points? Oh, never mind.
Well, I didn't do a 3-point, I did a center point.
See that?
Lots of different kinds of arcs. See, you click on the arc, you get all kinds of different
Which way
kinds
you
of arc.
want? Oh,
But-
okay.
Well, it
Yeah.
depends what you're doing, right?
There you go.
But you gotta make yourself an arc, and then we're gonna make a
I
straight
hope it's
line.
enough. If not,
Okay?
we can drag,
And I'm
right?
gonna make a straight line that goes like this. Okay?
Oops. Oh, yeah, I can.
So I have a line, and since I'm gonna wanna do a little bit of revolution here, right? I'm gonna make a surface of revolution, or at least part of a surface of revolution. I need something to revolve around, and that means I need a center line. So we're gonna have a center line, go up here and get a center line. And I'm gonna put a center line right here through the origin. Okay, now I probably ought to dimension this a little bit, so let's get a dimension. I'm gonna put a radius on this. Let's see, what sort of radius should I put on there? Oh, I don't know.
10
Let's
inches.
see, I think you said 10 inches. Well, I don't wanna do 10 inches, so we're gonna do what? We're gonna do
What
12
big one?
inches, right? So we'll look really different, just to be different here. Okay? And then I have some other thing that I need probably to put a dimension on, from maybe from here to here, right? And let's see, it was gonna be like, what, 48 inches long?
Yeah.
We'll make it 50, so I want 25 of it here.
Okay.
Okay? So that's, I will argue that's what, half a tank?
Yeah.
Half a tank,
Yeah,
right?
why not?
Tanks for the memories? Okay. Okay, so, keep using bad lines again, they'll get rid of it. So, I think, let's see, we made a line, oh no, 2 lines and an arc. Okay, so, okay, we're gonna get out of the sketch here. And now I wanna make a surface out of this. And if I go over to features over here, it's gonna wanna make me solids. Right, and I don't want a solid. So we have to go up here to insert, surface, and revolve. Okay. So we go up to the file at the top, we do insert, surface, and revolve. Right, because I want to play with surfaces. Right, and it goes, oh, I want to revolve that, and I don't want 360 degrees. I'm going to only go for.
So did you select a plane, or was yours already?
No, it was.
Because I got this weird message saying select a plane on which to sketch future cross section
Yep,
or
yep.
the
You need to,
existing sketch.
you need to, whenever you sketch, you need to, you have
Yeah.
a plane selected first. So I picked the.
I had the front plane selected.
Well, it didn't think you did for whatever reason, so
Rude.
go do it again. It's being crude, rude, and lewd, right? Which is what it does, so I have
Okay.
I will make an argument that that's 1/8 of a pressure vessel. We gonna buy that?
Sure.
Okay? Because I think if I had 4 of those around, I'd have a half a pressure vessel.
So 1/8 of it, not 1/8 scale?
No, it's not 1/8 scale, 1/8 of it.
Oh.
Okay? And we only need to model 1/8 because it's a pressure vessel and we have symmetry. So part of the process of doing it in this class is we're gonna learn how to apply symmetrical boundary constraints. Okay, because the tank is symmetrical, right, about any of these. It's a symmetrical about this line over here, because I only modeled half of it. right? And it's symmetrical about this plane over here, and it's symmetrical about this plane over there. Right. Okay, we buying that?
Can't get my turtles.
Okay, so we're all gonna accept that, or are you guys gonna argue with me? No, it's easy class today.
Sure.
Those UWB students that argue with me. They had fun today. Gave them a 3-hour midterm. They gave me 120 pages I have to grade. I think they got the better part of the deal. I'd rather spend 3 hours taking the exam than all weekend grading it, but. Okay, so we're happy with this. I'm gonna say, okay. I have my surface. I can whip it around, look at it, say cool things about it, and go, okay, I like that. And, right? And then we're going to go, well, now we need to do our simulation, right? Because we're gonna go do a little FEA on this thing. And I'm gonna go to the new study, yep. And we're gonna do a static one here, right? We'll do a static thing, and we can name it if we want to. Go, pressure. 1, oh, come on, I typed you in something. 1, and it didn't like me. Okay, and so we have a study, and we've been here before. You guys been at these pages before? Been here before?
Simulation? Which page?
Simulation?
What?
I think you have. And see, now, one of the things you notice that's different than it was before is if we look at our part, it's not a solid. What is it? It's a wavy thing that looks like a surface, right? This thing over here, that's our part. And instead of saying material not defined, it says thickness not defined, because I didn't tell it how thick it was. Okay? So, I get to go tell it how thick it is now, right? And I could do that by just going on here and going, okay.
Okay.
Come on. Ask for material, right? What are we gonna make it out of? Steels? Yeah. Might as well make it out of A36. No reason to make them out of good cold rolled steel, because how is the tank put together?
45 degree.
What kind? Piece by piece?
Yeah, it is put together piece by piece. How do we assemble the pieces? We weld them. So if there's any cold work in it, they're gone. Now, there is an exception,
Like this?
and that is if you make real high pressure vessels. High pressure, like if you make high pressure gas bottles for, oxygen or nitrogen or whatever you are, the big ones that sit on the round of the back of trucks, right? These are low pressure vessels. They'll only go up to a few hundred PSI. If you're gonna go up to a few thousand PSI, you don't weld them. Because when they fail, it's a real bad deal, right? Incredible amounts of stored energy in compressed gases, and when they fail, they've been known to, really ruin people's, lives, actually.
Isn't that typically when they go to filament wound tanks? Or
What's that?
isn't that typically when they go to filament wound tanks?
Well, you can go to filament wound if you get lighter. It was originally done to try to get lighter. So the original filament winding was you're trying to reduce the weight. It's all tensile, because of course the thing's trying to go boom. So they actually do pretty well for filament winding, but on high pressure vessels, they'll forge them, and there'll be a one piece of forged metal. The big ones that you move around are steel. If you're weight sensitive, you try to do them out of aluminum, and then they filament line the aluminum ones, which is typically what they're trying to do, is filament line the aluminum. Mostly take the hoop stresses, but, and that is done. They test them all. If they get high pressure ones, and even the low pressure ones are usually tested hydrostatically. That is, you fill them with a fluid and then put a little bit of gas in them or pressurize the fluid. And that's because if it goes boom, it just leaks a little bit of fluid. And because the fluid is essentially non-compressible, there's not a lot of stored energy in it. So it doesn't hurt anybody. When they're compressed full of gas and they go boom, again, it's bad news. So anyway, these are gonna be welded, so we can use A36, it's perfectly fine material. I can also edit the definition here. And as part of the definition, it will ask whether it's thin or thick, okay? You can do thick shell analysis with these elements. The thick shell analysis assumes that the stress is not uniform through the material. We assume that we basically do a cylindrical analysis. We assume it's a little higher on the inside than it is on the outside, a non-uniform stress distribution through the cross section. For most of what we do, thin shell analysis is fine. It's going to get you close enough. And let's be honest, are we going to be perfect with any of them? No. So hey, let's do the thin one that gets us close enough. And it does assume uniform stress distribution. I give a thickness here, and I'm going to give the thickness of, in my case, I think I'm going to go, how about 78? Just because I'm going to be stubborn and different today. Okay? So,
How
I'm
did
going
you get there? Sorry, I need time. How do you get to the thickness part?
you just right click on it and then go edit the definition.
Oh, edit definition, got it.
Okay? So, we have our perfectly good pressure vessel here. It looks really cool. And now we need to put a load on it, right? Well, we can put a load on it. We need to put what? Loads and boundary conditions, right? We know the routine now. I gotta put loads on it, I gotta put boundary conditions, and I gotta mesh it, and then we're gonna go see if we like the numbers. Okay? Right? Isn't that the routine?
Yes.
I mean, this is fourth week.
Yes,
You've
yes,
seen
yes,
me
yes.
do this,
Yes.
what,
Well, we
buddy?
use thin.
8 times? What's that?
Why we use thin material?
We use thin, yeah, because it's not gonna be very different. The stress gradient across it's very small, okay, and it will be close enough.
Constant. You want it
It's
constant.
most of the time we do use thin. Mostly this way certainly will agree with our numerical analysis, because our numerical analysis will assume a thin shell unless we wanna go do a thick shell analysis. Now, you can use thick and go check it with a thick shell hand analysis. Or you can use the thin shell assumption and go check it with a
Then,
thin shell analysis. Now, which one do you wanna do?
No, no,
the thin,
Which one do we think is gonna be easier?
Thin
shell analysis.
Thin shell analysis is gonna be a lot easier, right? Because a uniform stress assumption makes life a whole heck of a lot easier. We don't have to do some sort of gradient and figure what the inside and the outside are and all the rest of that sort of stuff, right? When it's uniform, then stresses are the same everywhere. And let's be honest, as the shell gets thin, well, I've got a thing that's what? I've got a thing that's, has a diameter of what, 24 inches and a wall thickness of about 80 thousandths or less than 80 thousandths of an inch, right? So that's a ratio of what, 240 to 1? The diameter to the thickness. Okay, I think that's big enough to support it. Typically, we say we can do thin shell analysis when it's over 10 to 1. Okay, well, I'm at 240 to 1. I think I can safely say that we're gonna get away with a thin shell analysis on this particular part. And that's usually true, because the materials we have are pretty strong, so it's usually the case. So now we need to do, which one do you wanna do first? Boundary conditions or loads?
Yeah.
Yes.
Yeah.
Boundary, okay. Well, we have to do symmetry boundary conditions on this, right? This part is symmetrical, the way we've modeled is symmetrical, and I insist you model it symmetrical because I'm a mean instructor. Okay, so we have to do symmetry boundary conditions on these, and means we're gonna have to put boundary conditions on the 3 symmetrical borders. Okay, and one of the parts of this exercise is what are symmetrical boundary conditions, what do they look like? And the way we do symmetrical boundary conditions is I'll pick on an edge like this one over here. It's behind itself, and I can do advanced fixtures, right? And it's already selected the edge. And then I'm going to do some geometry here. Select my geometry for this guy. And I really badly for this one want to pick the right plane. Okay? And I want to pick the plane in which I'm going to fix the out of plane displacement. Okay, so if I pick the right plane here now, what does symmetrical mean? It can't move that way, it can't move this way, it's gonna stay in this location, right? I'm gonna fix this location so it can't move either way. Because as it grows, what's it gonna do? Well, the amount that side grows and the amount that side grows over there are gonna be equal because it's symmetrical. Right, so I can fix this. Symmetry is when we have symmetry, the perpendicular planes, the symmetry don't remain perpendicular, right? So if I'm gonna fix this part here, I'm gonna use this plane as my reference plane such that I can fix the perpendicular one. Now, that's not the only part of the symmetrical boundary condition, okay? So I can come down here to my boundary conditions and I can fix I fix the out of plane boundary condition, right? And it doesn't give me any arrows, or it gives me arrows that are really small. So I'll have to go fix the arrows. Let me make the arrows big, right? Okay, come on. You're only 100%. Let's make them about 400%. Did my arrows get bigger? Still not very big.
I see.
500. Let me go to 500.
Selected the plane.
Yeah, you haven't selected anything, so the arrow's not.
Oh, okay. It's not, I selected the right plane. I thought I did. Okay, there we are. Okay, big arrows. Okay. I got big arrows. So you think those are too big? Yeah, I'll get back to 200. Okay, so we got big arrows, right? So that selects the out of plane boundary, right? So that's part of a symmetrical boundary condition, okay? There's another part of the symmetrical boundary condition that's in here. But guess what? It's gonna be continuous across here. The slopes are going to be continuous across it. It's not gonna bend like this when it goes across here, right? It's not gonna get discontinuous. They're gonna remain smooth, right? That things that are out of plane at those conditions are gonna remain out of plane at those boundary conditions. The way rotations work is that those are considered the out of plane boundary conditions. And so I need to fix those rotations, and those are these two here. This one here and this one here. Okay? This one here is the in-plane rotation. Right? Remember, when we define a rotation, we're defining the axis about which it rotates. The axis about which it rotates. That's what we're defining. And what this allows it to do is it allows it to move in the plane. It can move in the plane, in and out. The tank can get bigger. And it can actually rotate this way in the plane as long as this cross-section remains in the plane. What it can't do is it can't rotate out of the plane. We've got this plane here, it can't bend this way, right? Can't have those out of planes bending. That's called a symmetrical boundary condition. What we have done is we've fixed the out of plane translations and we fixed the out of plane rotations, okay? And the way they're described is if we pick our definition plane correctly, we get we fix the out of plane translation and then the opposite rotations. Okay?
So that plane can rotate